a telescope so powerful it can peer into the very cradle of the universe, capturing light that's been traveling for over 13 billion years. The James Webb Space Telescope, humanity's most advanced cosmic eye, has done just that, and what it found has turned the world of astrophysics upside down. In July 2025, JWST unveiled images of a galaxy so ancient, so impossibly structured, that it defies the laws of physics as we know them. This isn't just a discovery, it's a cosmic bombshell that challenges everything we thought we knew about the universe's birth. Buckle up, because this story is a wild ride through deep space, deep time, and the deepest mysteries of existence. Smash that like button, hit subscribe, and let's dive into the greatest cosmic enigma of our time. Why should you watch until the end? Because this isn't just about a distant galaxy. It's about rewriting the story of the cosmos, rethinking the origins of life, and questioning the very nature of reality. We'll explore how this discovery is shaking the foundations of science, sparking debates about dark matter, black holes, and even the possibility of ancient alien civilizations. Plus, we'll uncover what it means for humanity's place in the universe. Got your curiosity piqued? Let's get started. In the summer of 2025, the James Webb Space Telescope turned its infrared gaze toward a distant patch of sky, a region known as the Cosmic Dawn, a time just 400 million years after the Big Bang, when the universe was a mere infant. Astronomers expected to see the faint glow of the earliest galaxies, small, chaotic clumps of stars and gas, still coalescing in a turbulent primordial soup. These were supposed to be the building blocks of the cosmos, rough and unrefined, born from the raw materials of hydrogen and helium left over from the Big Bang. But what JWST captured was something entirely different. A galaxy so massive, so structured, and so mature that it seemed to belong to a universe billions of years older. This galaxy, nicknamed the Impossible Galaxy by awestruck researchers, was a cosmic paradox. Its spiral arms, elegantly coiled and teeming with star-forming regions, stretched across light years, orbiting a luminous central core. Its light signature, analyzed through JWST's spectrograph, revealed the presence of heavy elements like carbon, oxygen, and even traces of iron. Elements that should only exist after generations of stars have lived, died, and scattered their ashes in supernova explosions. According to the standard model of cosmology, such a galaxy shouldn't exist in a universe so young. It was as if JWST had photographed a fully grown adult in the cradle of a newborn. The implications were immediate and profound. This wasn't just a curious anomaly, it was a direct challenge to the bedrock of astrophysical understanding. The early universe, according to our models, was a chaotic place, a fog of particles and radiation still cooling from the Big Bang's fiery birth. Galaxies were supposed to be small, irregular, and dominated by massive, short-lived stars that looked nothing like the majestic spirals we see in today's cosmos. Yet here was a galaxy that appeared to have skipped billions of years of evolution, standing tall and fully formed when the universe was barely 400 million years old. Let's break this down. How could a galaxy this complex exist so early in cosmic history? To understand the mystery, we need to dive into the science of cosmology, the study of the universe's origin, structure, and evolution. The standard model, known as the lambda cold dark matter, lambda CDM model, describes a universe that began with the Big Bang 13.8 billion years ago. In its earliest moments, the universe was a hot, dense plasma of particles and radiation. As it expanded and cooled, hydrogen and helium atoms formed, eventually clumping together under gravity to create the first stars and galaxies. These early galaxies were expected to be small, chaotic, and metal poor, meaning they contained mostly hydrogen and helium, with only trace amounts of heavier elements, or metals in astronomical terms, forged in stars. Over billions of years, stars would live and die, enriching the cosmos with elements like carbon, oxygen, and iron through supernova explosions. These elements would then become the building blocks for more complex galaxies, stars, and even planets. According to this timeline, a galaxy as structured and chemically rich as the Impossible Galaxy should have taken at least 2 to 3 billion years to form, yet it existed when the universe was less than 400 million years old. The galaxy's structure was equally baffling. Its spiral arms were not the disordered swirls of early cosmic flotsam, but tightly wound, stable features orbiting a luminous core. Such complexity requires time, gravity, and interaction interactions. Processes like galactic mergers, tidal forces, and internal feedback mechanisms that sculpt galaxies over hundreds of millions, if not billions, of years. Even more astonishing, the galaxy's light curve, the pattern of its brightness over time, suggested the presence of an active galactic nucleus, possibly powered by a supermassive black hole. Black holes of this size were thought to take billions of years to grow, yet here was evidence of one in the universe's infancy. The chemical composition added another layer of mystery. JWST's spectrograph detected signatures of carbon, oxygen, and iron in quantities that implied multiple generations of stars had already cycled through their lives. For these elements to be present, stars would need to have formed, fused hydrogen into heavier elements, exploded as supernova, and dispersed their material, all within a cosmic blink. This scenario seemed implausible, suggesting either an accelerated stellar life cycle or an entirely unknown mechanism for elemental formation. The discovery of the impossible galaxy wasn't just a single data point, it was a scientific earthquake. It sparked a frenzy of debate, with researchers around the world scrambling to explain how such a galaxy could exist. The implications were staggering. If galaxies like this were forming so early, the entire timeline of cosmic evolution needed a rethink. Scientists began exploring a range of possibilities, each more radical than the last. One hypothesis focused on dark matter, the mysterious substance that makes up about 27% of the universe's mass energy. Dark matter is thought to provide the gravitational scaffolding for galaxy formation, but its role in the early universe was assumed to be relatively simple, guiding the collapse of gas clouds into stars and galaxies. Could dark matter have played a more dynamic role, accelerating the formation of massive galaxies? Some models suggested that dense clumps of dark matter could have acted as gravitational wells, pulling in gas and triggering rapid star formation far earlier than expected. Another possibility was a flaw in our interpretation of redshift, the stretching of light as the universe expands. Redshift allows astronomers to estimate the distance and age of cosmic objects, but if our assumptions about redshift were incorrect, we might be miscalculating the age of these galaxies. This could mean the impossible galaxy wasn't as old as it appeared, though this explanation struggled to account for its chemical richness and structural complexity. More daring theories ventured into uncharted territory. Could the laws of gravity behave differently in the early universe, allowing for faster galaxy formation? Some physicists proposed modifications to Einstein's general relativity, suggesting that gravity might operate differently at cosmic scales or in high-energy environments. Others speculated about the influence of parallel universes or higher dimensional phenomena, where structures from other realms could leak into our own, creating the illusion of impossible galaxies. Perhaps the most provocative idea was that the universe itself might be older or more complex than we thought. Some researchers revisited the concept of a cyclic universe, where our cosmos is just one in a series of expansions and contractions, each leaving subtle imprints on the next. Could the impossible galaxy be a relic from a previous cosmic cycle, preserved through unknown physics? While speculative, these ideas were no longer dismissed outright. They were necessary to explain evidence that refused to fit within existing models. As JWST continued its mission, the impossible galaxy proved to be just the beginning. Follow-up observations revealed more galaxies in the same early epoch, each displaying similar characteristics. Too large, too luminous, too structured for their age. These weren't identical clones, but they shared a common thread: developmental anomalies that defied the standard timeline. Some showed unusually high concentrations of heavy elements, others had complex morphologies like barred spirals, and a few exhibited synchronized starburst activity as if triggered by an external signal. The statistical improbability of so many anomalies eroded the argument that these were mere observational errors or instrument glitches. This wasn't a single outlier. It was a pattern, a hidden chapter in the universe's history that had gone unnoticed until now. The galaxy's isolation was particularly striking. Unlike modern galaxies, which form in dense clusters connected by cosmic filaments, these early galaxies often stood alone, untethered from the usual web of gravitational interactions. Their pristine surroundings showed no signs of past collisions or disruptions, suggesting a formation process unlike anything observed in the local universe. The galaxy's chemical compositions were equally perplexing. In addition to carbon, oxygen, and iron, some showed traces of magnesium, silicon, and even platinum, elements that require intense stellar recycling cycles. One radical hypothesis proposed that these elements weren't formed in stars at all, but through primordial particle interactions, perhaps involving involving exotic physics in the universe's first moments. If true, this would mean the early universe could host chemistry as complex as our own Milky Way, not through stellar evolution, but via mechanisms we've yet to discover. The discovery of these galaxies didn't just challenge cosmology, it opened new doors for the search for extraterrestrial life. If galaxies were forming faster and with greater chemical complexity, the building blocks for planets, rocky elements, water, carbon compounds, could have existed billions of years earlier than thought. Earth, at 4.5 billion years old, is a relative newcomer to the cosmic stage. These findings suggest that habitable conditions might have existed in other galaxies when our planet was still a molten speck, dramatically extending the window for the emergence of life. Astrobiologists were particularly intrigued by the detection of chiral particles, molecules with a specific orientation in some of these galaxies. Chirality, or handedness, is a key feature of life's building blocks, like amino acids and sugars, which favor one orientation over another. If the early universe had a chiral bias, it could mean that the chemical foundations of life were written into the cosmos from the very beginning. This would make life not a rare fluke, but a universal feature, potentially widespread across these ancient galaxies. The possibility of ancient biospheres sparked a wave of speculation. Could these galaxies have hosted long-dead civilizations, their signals lost to the vastness of time? Signals previously dismissed as noise were re-examined, and astrobiologists began to consider the possibility of life that rose and vanished before Earth even formed. This wasn't just about finding life now, it was about searching for echoes of life that might have existed billions of years ago, preserved in the light of these impossible galaxies. At the heart of the impossible galaxy's mystery lies the question of supermassive black holes. The galaxy's active nucleus suggested the presence of a black hole millions or even billions of times the mass of our sun. In today's universe, such black holes form over billions of years through mergers and accretion. But in a universe less than 400 million years old, their existence was a puzzle. How could black holes grow so massive so quickly? One hypothesis proposed that primordial black holes, formed in the universe's first moments, acted as cosmic accelerators. These black holes could have seeded galaxies by pulling in gas and triggering rapid star formation. If they had properties beyond those of modern black holes, they might have compressed matter and energy in ways that accelerated galaxy formation. Another idea suggested that cosmic strings, hypothetical one-dimensional defects in space-time, could have collapsed to form these black holes, creating the gravitational scaffolding for early galaxies. Gravitational wave simulations added another layer of intrigue. While detecting gravitational waves from such distances remains a challenge, models suggested that the impossible galaxy's black hole might have left unique ripple patterns inconsistent with standard merger scenarios. This hinted at an exotic collapse mechanism, perhaps involving unknown forms of matter or energy. If true, black holes could be more than just galactic anchors. They could be the architects of the early universe's impossible complexity. The discovery of these galaxies forced scientists to rethink the very framework of cosmology. The lambda CDM model, while successful in explaining many features of the universe, struggled to account for these anomalies. Researchers began developing new models, incorporating ideas like variable inflation rates, where certain regions of the universe expanded more slowly, creating conditions for rapid galaxy formation. Others explored the concept of cosmic time bubbles, where time flowed differently due to variations in spacetime's curvature, creating the illusion of accelerated evolution. The holographic principle, rooted in string theory, offered another provocative explanation. This idea suggests that the universe is a three-dimensional projection of information encoded on a two-dimensional surface. Could the impossible galaxy be a glitch in this cosmic projection, a fragment of deeper reality leaking through? While speculative, this concept bridged quantum mechanics, general relativity, and cosmology, offering a tantalizing framework for understanding these anomalies. The galaxy's spatial distribution also raised questions about cosmic topology, the study of the universe's large-scale shape. Unlike the uniform structure predicted by inflation, these galaxies appeared in loosely coherent clusters, suggesting an unknown influence shaping their formation. Some theorize that space-time itself might have localized properties, like phase transitions in condensed matter physics, allowing for faster structural development in certain regions. The James Webb Space Telescope, with its 6.5-meter mirror and unprecedented infrared sensitivity, is uniquely suited to uncovering these mysteries. Its ability to resolve individual star-forming regions and trace gas flows within galactic arms has given us a front-row seat to a universe that's far more complex than we imagined. Unlike its predecessor, the Hubble Space Telescope, JWST can peer through cosmic dust and capture light from the universe's earliest moments, offering a clarity that's rewriting the cosmic narrative. But JWST's role goes beyond observation. It's a catalyst for a scientific revolution. Its data has sparked cross-disciplinary collaboration, bringing together astrophysicists, quantum physicists, data scientists, and even philosophers to interpret a universe that no longer fits our models. Artificial intelligence tools are sifting through terabytes of data, uncovering subtle patterns that hint at a deeper cosmic structure, a fractal rhythm, or underlying symphony of form and energy. The impossible galaxy is more than a scientific discovery. It's a reminder that the universe is not obligated to be comprehensible. It challenges us to let go of our assumptions and embrace the unknown, where the impossible does not mean the untrue, but the undiscovered. As JWST continues to scan the cosmos, each new image brings more questions than answers, revealing a universe that's older, stranger, and more complex than we ever dreamed. This is a moment that will define astronomy for generations, a testament to the power of curiosity and the thrill of discovery. So what do you think of this cosmic enigma? Could it be evidence of a cyclic universe, a glitch in the cosmic code, or something even stranger? Drop your thoughts in the comments below, give this video a like, and subscribe for more mind-bending updates from the edge of the universe. The cosmos is calling. Let's keep exploring together. As we gaze at the impossible galaxy's ancient light, we're not just peering into the past, we're holding a mirror to our own ignorance. The James Webb Space Telescope has revealed a cosmos that defies our neatly crafted equations, reminding us that our understanding is but a tiny speck in the vast expanse of reality. This discovery invites us to embrace humility, to recognize that the universe is a puzzle with pieces we've yet to find. Imagine a cosmic tapestry woven with threads of mystery, where each new observation unravels another layer of the unknown. What if this galaxy is a clue to a deeper truth, one that could redefine not just astronomy but our very perception of existence? Share your wildest theories in the comments. What do you think lies beyond the veil of this cosmic mystery? This encounter with the impossible galaxy is more than a scientific milestone. It's the spark of a new renaissance in human thought. Just as the telescope of Galileo shattered the Earth-centric view of the cosmos, JWST's revelations are dismantling our assumptions about time, matter, and the universe's origins. Scientists, philosophers, and dreamers alike are uniting to grapple with questions that stretch beyond the stars. Are we part of a multiverse where countless realities intersect? Could the laws of physics be more flexible than we ever imagined? This discovery is a call to action for every curious mind, urging us to question, explore, and imagine. Hit that subscribe button to join this cosmic journey, and let us know in the comments how this discovery inspires you to rethink the universe. The light from the impossible galaxy captured by JWST has traveled billions of years to reach us, carrying with it a legacy that will echo through generations. This isn't just a moment for scientists, it's a gift to humanity, a chance to redefine our place in the cosmic story. As we stand on the cusp of this new era, we're reminded that exploration is not about finding answers, but about daring to ask bigger questions. What secrets will JWST uncover next? Could we find more galaxies that challenge our reality, or even signs of life that reshape our understanding of existence? This discovery is a beacon, guiding us toward a future where the unknown is not feared, but celebrated. The impossible galaxy sings a cosmic symphony, its light a melody composed in the fires of the early universe. Each photon captured by JWST carries a note from a time when the cosmos was still finding its rhythm, yet this galaxy's harmony is startlingly refined, as if played by an orchestra far older than its years. Its spiral arms, pulsing with star-forming regions, suggest a universe that was not a chaotic cacophony, but a structured composition from its earliest moments. This revelation hints at an underlying order, a set of cosmic rules we've yet to decipher, governing the dance of matter and energy across unimaginable scales. Could this galaxy be a fragment of a universal score, written in laws we're only beginning to hear? Standing at the edge of this discovery, we find ourselves peering into the very fabric of cosmic reality, where the boundaries of space, time, and possibility blur. The impossible galaxy suggests that the universe might not be a single, linear narrative, but a tapestry of overlapping stories, each woven with its own rules and rhythms. Some physicists now wonder if this galaxy is a glimpse of a space-time pocket, a region where the laws of physics bent in ways we cannot yet model. It's as if JWST has caught a fleeting shadow of a reality beyond our own, a place where galaxies form not by chance but by a deeper, unseen design. This encounter pushes us to question whether our universe is one of many, each with its own cosmic script. Beyond the data and equations, the impossible galaxy whispers an eternal question. Why does the universe exist as it does? Its existence, so defiant of our expectations, challenges us to look beyond the mechanics of stars and galaxies to the purpose, or lack thereof, behind the cosmos. Is this galaxy a random quirk, a statistical outlier in an infinite sea of possibilities? Or does it point to a purposeful complexity baked into the universe's foundation? As JWST continues to unveil these cosmic enigmas, it invites us to wrestle with the profound, to ponder whether the universe is a machine, a dream, or something far stranger. This discovery is not just about what we see, it's about why we seek to understand at all. The impossible galaxy serves as a bridge across cosmic time, connecting the universe's infancy to our present gaze. Its ancient light, captured by JWST's mirrors, tells a story of a cosmos that was already weaving intricate patterns when it was barely born. This galaxy's existence suggests that the seeds of complexity, galaxies, stars, perhaps even life, were sown far earlier than our models predicted, hinting at a universe that was never truly simple. It's as if the cosmos was born with a blueprint, a hidden framework that guided its evolution from chaos to order in mere hundreds of millions of years. This discovery challenges us to imagine a universe where time itself is not a straight line but a river flowing at different speeds, carrying secrets that JWST is only now beginning to uncover.